conversational AI are systems that can listen and talk to us.
Can you talk to me in a brain rot way?
Absolutely, darling. What's on your mind?
All of these real-time systems run off your phone or computer because of many reasons, but mainly because of computational constraints when it comes to decoding and encoding audio data streams. Today, I'm going to build a real-time conversational AI on an embedded system, the SenseCap Watcher, which has a microphone, a speaker, a camera, and most importantly, an ESP32 S3 with 8 megabytes of pseudo-static RAM and 32 megabytes of flash.
Not only that, I'll make it act and sound like Wheatley from Portal 2.
Ah, that's a classic! I'm Wheatley, your friendly neighborhood AI. Sort of like a sidekick who's always ready to trip over a power cord.
The SenseCap Watcher is the star of the video today. It's an open source physical AI agent developed by Seed Studio. Using it, you can deploy agentic systems that leverage both image input and audio input. For example, recognizing people if they wear masks or not when coming into an office. Its firmware is pretty cool, but most importantly, it is open source, which is the reason why I bought it, to hack it to do other stuff for me. The folks at SenseCap was kind enough, they not only open sourced their firmware, but many other use cases. For example, this OpenAI real-time conversation with Pepe the Frog written with ESP32. Thanks to this, our job gets a bit easier, not a lot easier, which I'll explain in the next few sections. To build Wheatley, we need two components, the front end and the back end. The front end is basically making the device look like Wheatley, which is rather trivial. The back end is making it talk and behave like Wheatley, which I can tell you is not trivial at all. The SenseCap Watcher has a 412x412 LCD display. It is run with a library called LVGL, which, if you don't know, powers a lot of devices around you. It's basically an incredibly light rendering engine, which helps you build GUI, same as with HTML and CSS, on small embedded systems. All you need to do to port it to any system is to provide a function which draws pixel on the screen. There is a good amount of documentation for this already. All I had to do was to draw Wheatley eye in Procreate, split it in layers to support animation, for example, like closing the eye, linking, then convert it to CRAs, which is supported by LVGL. To make the eye interactive, I had to make a state machine, which has 4 states: listening, speaking, on, and off. Switching between the states will help the device animates the eye so it looks interactive. As you can see here, I also built simple functions to interact with the device manually, changing the opacity of the pupil, its position, and the distance of the eyelids. Now, when it comes to making the AI sound and behave like Wheatley, it is really hard. At first, I thought it was just a walk in the park. We already had the OpenAI example from before, but it was not. First, to make the AI sound like Wheatley, we need to train an AI model with Wheatley voice. Second, to make the AI act like Wheatley, we need to provide it with instructions. Two of these cannot be done at the same time with OpenAI real-time APIs. Therefore, we need to decouple this voice generation process. For text-to-speech, I used ElevenLabs and made a voice using an hour-long video of Wheatley talking. For speech-to-text, I used OpenAI Whisper model, and for the LLM, GPT-4o. Now, if you notice already, these 3 components by themselves aren't real-time. We need to somehow combine them. For this, we have LiveKit. It allows us to customize any real-time AI system to use our components. But bear with me, this isn't the hardest part. The hardest part is making LiveKit work within ESP32 because its API is nothing like OpenAI. To explain this, I have to give you a crash course on WebRTC. Real-time AI systems leverage WebRTC to stream data back and forth fast. It works by transferring data using a peer-to-peer connection between 2 devices. The process for connecting the devices itself is not covered by the WebRTC specification, but it's covered externally with a process called signaling. This basically means exchanging contact information on the internet. To communicate on the internet, we use IP addresses. However, these addresses are quite limited. So in the modern world, we normally use the internet with network address translation, which basically translate a public IP address to your private IP address. This worked well with client-server architecture, but in peer-to-peer, it hindered devices from connecting directly to each other. There's a solution for this, which is called IPv6, but not that widely used. Therefore, to support peer-to-peer connection, we need to somehow bypass NAT and find out a way to connect two devices directly. This is done with ICE, which use stun or turn, all these terms you can search online, and the connectivity information is delivered over a WebSocket or a protocol of choice. This process is called signaling. The reason I have to mention this is because each real-time system have their own way of signaling. In the case of OpenAI, they have an endpoint which we can seamlessly connect to. It's pretty standard. In the case of LiveKit though, they developed their own signaling protocol over WebSocket. So we can't use the OpenAI example you have from Seed Studio from before. Now, good news, the CTO from LiveKit was kind enough to have a so-called unofficial embedded SDK. Wow, so that means if I write a way to handle the audio on the SenseCap and use this SDK, it should all work, right? Oh, no, it was a lot of pain. It was a long pain. First, to handle audio, we need to understand the codec of the microphone and speaker on the SenseCap. This part was rather easy. I just need to reverse engineer some of the code. Then we need to figure out a way to transfer this data to a codec which is supported by LiveKit. And in this case, it's called Opus. This is done with an Opus decoder and encoder. To make this work, I need to spend some time back and forth reverse engineering again, both the LiveKit embedded SDK and the SenseCap specification, which is not fun at all.
I'm crying, mate.
Furthermore, to make matters worse, unlike other WebRTC application, it sends audio signal even when there's no audio. For example, when your AI says literally nothing, the ESP32 will still receive audio packets. Now, why is that a pain? Well, if you remember, we also have an UI part of the project, and the UI animation requires a lot of memory as well as compute power. Every time I try to run the UI along with the LiveKit connection, it closes the WebSocket after 15 seconds of establishing the connection with no error but a warning. And now that drives me crazy, because I didn't know it was the UI fault. I had to delete things gradually, and when I started to get to the UI, it suddenly worked. Now I don't know fully the reason behind this, but I can say that when the UI runs, it often occupies 100% of the CPU. And there might be some time specification that was not satisfied. Remember that we are building on ESP32 and we're using the free RTOS. So there are tasks, there are concurrencies. Furthermore, it might use memory stored in the PSRAM, which use the SPI lines, same lines as the displays, and more equipment inside the SenseCap, which a fault in timing can result poorly. Debugging this further requires going way deeper, and so my method for now is to don't let the UI run. And there it is, we have the first open source real-time conversational AI running on an ESP32 using LiveKit. Cherry on top of the cake, it sounds and act like Wheatley.
I don't want to listen to you.
No problem at all. I'm like a badly tuned radio. Easy to tune out.
Wait.
Oh, I'm like a cat. I can't resist a good pause. What's the last
Can you introduce yourself?